Welcome to Module 1 of the Data Center MEP Testing and Commissioning Playbook. In this module, we'll focus on commissioning governance, level gates, and the electrical power path. We'll cover the entire workflow from the initial design review, or CxL0, all the way through to CxL5, which involve the installation and testing of high, medium, and low voltage power systems, transformers, UPS, batteries, and containerized electrical plants. You'll see the process broken down into key stages: design review, factory acceptance testing, installation quality checks, pre-energization static tests, startup, site acceptance testing, and finally, handover and training. Each stage plays a critical role in ensuring that electrical systems meet Tier 3 and Tier 4 standards for reliability and performance. Our training will emphasize commissioning governance and the use of tag gates to track progress, provide clarity on expected evidence at each stage, and demonstrate how to manage 150 kV high voltage and 20 kV medium voltage power systems. We'll also dive into specifics around transformers, UPS units, batteries, and the unique aspects of containerized electrical plants. This module is structured to serve as a video chapter, where I'll first explain the concepts, then present the evidence you should expect at each stage. We'll also pause for practical examples like test packs or real-world field scenarios to help you solidify your understanding. Let's get started. Here we have the table of contents for Module 1 of our Data Center MEP Testing and Commissioning Playbook. This module is structured to serve as a clear guide through the entire training, with each section functioning as a chapter marker for easy navigation. We start by discussing how to use the playbook effectively and outline the expected training outcomes. Then, we move into the commissioning philosophy along with governance and the relevant standard stack, which sets the foundation for everything else. Next, we cover the correlation between tier and rated 3 to 4 levels and the evidence required for resilience. Following that, we dive into the different commissioning level gates from CxL0 to CxL6, including tag governance, which is critical for project management and quality assurance. Electrical power path coverage is next, focusing on the matrix and readable schematics essential for understanding the electrical layout. We also explain important high voltage and medium voltage terminology, along with commissioning at level CxL1 and factory acceptance tests for transformers and batteries. The training continues with detailed coverage of cables, bus ducts, UPS systems, static transfer switches, automatic transfer switches, PDUs, and monitoring proofs to ensure reliability. We then look at containerized MV equipment, including RMUs, PTUs, and generator plant commissioning. Finally, we conclude with an integrated electrical commissioning item register, keep track of all the components involved. A key rule emphasized throughout is that every test item must be traceable to a design basis, a commissioning level gate, an acceptance criterion, a calibrated measurement, and a signed evidence record. This traceability ensures thorough documentation and accountability across the entire commissioning process. This playbook is designed to provide a clear and repeatable path for MEP commissioning, guiding you from the initial design review all the way through to operational transition. Its main goal is to turn each level of commissioning into concrete evidence, with acceptance criteria and sign-off gates to ensure nothing is missed. This approach helps engineers fully understand what must be proven before any equipment or system can move forward. The intended audience includes commissioning authorities and managers, project and construction managers, QA/QC teams, engineers of record, vendors, and specialist contractors, as well as operations and maintenance teams who eventually take over the facility. When using this playbook, always rely on project specifications, local laws, authority having jurisdiction requirements, and manufacturer instructions as your guiding standards. If there are any conflicts between standards, the most stringent requirements should be adopted unless you have formal approval otherwise. It's crucial to record every issue and make sure all are resolved or formally accepted before moving to the next gate. At its core, this playbook functions both as a training manual and a practical project guide. It should be tailored to fit your approved design, site constraints, safety protocols, and authority requirements. The organization follows commissioning levels first, then major MEP disciplines, and finally includes templates and schematic examples. Remember, a commissioning level is more than just a scheduled milestone. It's a controlled, documented package of evidence showing readiness to tackle higher risks. Consistency is key, So use the same naming conventions, tag numbers, drawing references, and equipment IDs across all scripts, checklists, building management system points, photographs, and issue logs to maintain clear communication and tracking throughout the project. After completing this training, engineers will have a clear understanding of the different commissioning levels from CxL0 through CxL6 and what must be accomplished at each stage. We'll cover how to develop a commissioning schedule starting with the operational readiness and go-live milestones and working backwards to ensure all tasks are properly aligned. You'll learn how to write and review essential documents such as test method statements, checklists, and various test scripts, including site acceptance testing, hardware loop testing, and integrated system testing with clear pass or fail criteria. We will also focus on applying a tag-based readiness process that safeguards both safety and quality without any shortcuts. It's important to associate the commissioning evidence with industry standards like Uptime Tier 3/4 and TI 942 rated 3 or rated 4, ensuring resilience requirements are met. Additionally, you'll be able to identify the minimum mechanical, electrical, and plumbing evidence needed for successful handover, training, and operational acceptance. The training is structured to cover key process controls, including different levels, tags, roles, responsibilities, and scheduling. Then we move on to the technical proof aspects like load testing, transfer procedures, control mechanisms, and failure handling. Finally, we'll focus on achieving operational readiness by addressing training needs, operations and maintenance, spare parts management, and a computerized maintenance management system. This comprehensive approach ensures that after the training, engineers are well equipped to manage every aspect of the data center MEP testing and commissioning process effectively. Now, we're diving into Section A, which focuses on the commissioning framework and governance. This section outlines a controlled, evidence-driven process that guides us from the initial design phase all the way through to operations. Essentially, it's about ensuring that every step is carefully managed and verified to meet our standards and expectations. This framework helps us maintain quality and consistency across all aspects of data center MEP. That's mechanical, electrical, and plumbing, testing, and commissioning. By following this playbook, we create a reliable, well-governed process that supports successful project delivery and long-term operational excellence. Let's talk about our commissioning philosophy. Commissioning isn't just about passing a single test at the end. It's a progressive chain of evidence that builds confidence step by step. Starting from the design intent, we rely on documents like the owner's project requirements, basis of design, and statement of operation to guide us. Then we move into verifying the installed quality through quality assurance and control, using static tests to ensure everything is built as specified. Next, we ensure the equipment is ready through pre-functional startup activities. Once that's confirmed, we perform system-level testing with site acceptance tests and heat load tests to prove performance. We also include integrated system testing, which focuses on failure modes to confirm system resilience. Finally, we make sure the system is operations ready by conducting thorough training and completing a formal handover. A core principle here is that each stage must address and close out any risks or issues left from the previous phase. All evidence must be traceable back to approved documentation, from drawings and permits to calibration certificates and issue closures. Controls, alarms, and data trending are just as crucial as mechanical and electrical operations because they demonstrate observability. We also emphasize strict gate discipline. Systems should not advance simply due to schedule pressures. They only move forward when acceptance criteria are fully met, or there is a documented exception with defined risk, mitigation, and an expiry. Any deficiencies that impact safety, performance, operation, or evidence must be resolved before progressing to the next gate. This approach ensures a reliable, safe, and well-documented commissioning process. Here we have an overview of the lifecycle and gate model for data center MEP testing and commissioning. The process is divided into distinct phases, each with specific commissioning levels, objectives, and exit criteria. Starting with the design phase, labeled from CxL0 to CxL1, the main goal here is to establish the design intent, controls, and testing strategy, as well as conduct factory-proof testing. The exit evidence for this phase includes the commissioning plan, completed review comments, and factory acceptance or witness test reports. Moving on to construction phase, which covers CxL2A to CxL3, the focus shifts to verifying quality of installed systems, performing static tests, and ensuring individual equipment operations are correct. The documentation necessary to exit this phase includes tags, checklists, inspection records, and startup reports. Next is the acceptance phase, encompassing CxL4 and CxL5. Here, the emphasis is on proving system performance, ensuring redundancy, handling failure scenarios, and validating integrated resilience. Key evidence for this stage includes site acceptance tests, high-level tests, integrated system test reports, raw data, trending information, and resolution of any issues. Finally, the transition phase at CxL6 involves transferring all relevant knowledge, documentation, spare parts, asset data, and operational control to the client or facility management team. Exit criteria include comprehensive system manuals, operation and maintenance documentation, training records, and formal go-live sign-off. It's important to note that while gate terminology might vary depending on the project contract, the logical sequence remains consistent, moving from defining design intent through installation and energization readiness, startup, system proof, integrated proof, and ultimately full operations. This structured approach ensures a thorough and reliable commissioning process for data center MEP systems. On this slide, we're looking at the governance model and escalation process for data center MEP testing and commissioning. First, the owner or operator is responsible for setting acceptance priorities, taking delivery of the facility, and approving operational readiness. They ultimately decide when the project is ready to go live. Next, the commissioning authority or provider, or CxA/CxB, manages the commissioning process. They validate all evidence, coordinate system acceptance testing and integrated system testing, and recommend whether the project meets requirements for acceptance. The general contractor coordinates site execution, ensuring safety controls are in place, managing contractor resources, and maintaining accurate document uploads throughout the process. The engineer of record owns the design intent, reviews any deviations, and confirms that the technical aspects conform to the design specifications. Vendors and specialists provide specific methods, handle startup procedures, supply test records, set equipment configurations, and issue manufacturer acceptances, all critical for verifying that systems perform as planned. The operations team reviews the sequence of operations, witnesses critical tests, and accepts the training, spare parts, and operations and maintenance data needed for ongoing facility management. Importantly, the model highlights when escalation is needed. Specifically, any issues related to quality, schedule, design, safety, or acceptance risks must be escalated promptly. When a field issue arises, the escalation path can involve the CXA or QA/QC team, the project manager or construction manager, the engineer of record or subject matter experts, the senior project lead, and finally, owner acceptance. If there is any uncertainty about whether a condition requires escalation, the best practice is to escalate early. Include all relevant evidence, identify affected systems, specify the decision required, note any schedule impact, and recommend mitigation steps. This structured governance and clear escalation process ensures project quality and timely resolution of issues, which helps deliver a successful and operational data center. Here we have the standards and compliance stack for data center MEP testing and commissioning. The key point is that commissioning must verify the approved design, while also meeting all statutory, safety, and industry requirements. This starts with complying with local laws, obtaining approvals from authorities having jurisdiction, securing necessary permits, and adhering to environmental and fire safety regulations. Next, the project contract, owner's project requirements, basis of design documents, specifications, drawings, sequence of operations, and acceptance criteria all set the framework for what the commissioning must achieve. The data center resilience targets are critical too, usually aligning with Uptime Institute Tier 3 or 4 standards and TIA 942 rated 3 or rated 4 classifications, ensuring high reliability and availability. Commissioning best practices are guided by ASHRA Guideline 0, Standard 202, and the Building Commissioning Association's process attributes, supported by a detailed project commissioning plan. We also adhere to a variety of technical standards across electrical, life safety, mechanical, and controls disciplines, such as NETA, NFPA, EN, IEC, ANSI standards, OSHRI TC 9.9, and relevant local equivalents. Manufacturer instructions are another essential piece, covering factory settings, firmware, calibration, and test tolerances. Finally, whenever there's an overlap of requirements, the rule is to comply with the most stringent one unless an approved deviation is documented. This ensures we meet or exceed all necessary criteria for safe, reliable, and compliant data center operations. Now, we're moving into Section B, where we'll explore the correlation between tiers and rated resilience. This part focuses on how commissioning evidence aligns with the intent of uptime Tier 3 and 4, as well as TI 942 rated 3 and rated 4 standards. Essentially, we're mapping the testing and commissioning data to ensure these resilience levels are properly met. This approach is detailed in the Data Center MEP Testing and Commissioning Playbook, which serves as a guide to confirm that infrastructure performance matches the required tier and rated criteria. Understanding this correlation is key to maintaining robust and reliable data center operations. On this slide, we're looking at the correlation between uptime Tier 3 and 4 standards and the TI 942 rated 3 and rated 4 classifications, focusing on data center mechanical, electrical, and plumbing testing and commissioning. Starting with uptime Tier 3, it emphasizes concurrent maintainability. This means the data center has redundant components and distribution paths, allowing maintenance work without shutting down IT operations. To commission for this tier, you need to demonstrate planned isolation of each component or path while still supporting the critical load. TIA 942 rated 3 aligns closely with this concept, but specifically refers to concurrently maintainable site infrastructure. It requires redundant capacity components and multiple independent distribution paths, though typically only one path serves IT equipment at a time. The commissioning proof involves showing that every component and distribution element can be removed or serviced without disrupting ICT functionality. Moving to uptime Tier 4, the standard steps up to fault tolerance. This requires independent and physically isolated redundant components and distribution paths, ensuring that the system can handle planned and unplanned faults with no impact on IT operations. Commissioning must verify no common mode or cascading failures occur. Similarly, TIA 942 rated 4 represents fault-tolerant site infrastructure with redundant capacity components and multiple active distribution paths. Commissioning demands proving concurrent maintainability plus the ability to tolerate a fault anywhere without downtime. Finally, it's important to remember that this playbook uses the project's formal certification target as the controlling basis. It maps out test intent, but does not replace certification reviews by the relevant authorities. This ensures that all testing and commissioning align with the intended resilience level for your data center. Let's talk about the testing evidence required for rated or Tier 3 and Tier 4 data centers, focusing on two key concepts: concurrent maintainability and fault tolerance. Starting with Tier 3 or rated 3, the main goal is to prove concurrent maintainability. This means we need to demonstrate that planned maintenance can be performed without disrupting the information and communication technology systems. The testing approach involves isolating one path at a time in critical components like medium and low voltage switchboards, transformers, UPS modules, ATS and STS systems, power distribution units, chillers, pumps, controls, and network nodes. During this isolation, it's important to confirm that the remaining active path can handle the required load under the given environmental conditions. Additionally, the return to normal process should be controlled carefully. It shouldn't be automatic unless specifically allowed. Detailed records should be captured throughout testing, including timing, load, temperature, alarms, operator actions, and the exact sequence of restoration. Moving on to Tier 4 or rated 4, the testing requirements build on Tier 3 by also proving fault tolerance. This involves simulating single faults across active power systems, cooling, control systems, network, and fire or life safety interfaces. The test must verify that physical and logical separation is intact, ensuring no common mode failures and no cascading loss of capacity. Controls should fail safely, and automatic responses via alternative paths should activate as required by the Statement of Operations. Importantly, trend data before, during, and after each fault must be analyzed to confirm there are no unacceptable changes in temperature or power levels. In summary, these tests ensure that Tier 3 data centers can maintain operations during maintenance without disruption, while Tier 4 centers add an extra layer of resilience by demonstrating the ability to tolerate faults without service impact. Here we have a resilience evidence map that outlines the key testing and commissioning criteria for different systems in a data center, aligned with Tier 3 and Tier 4 levels of reliability. Starting with electrical utility and MV/LV systems, Tier 3 focuses on maintenance isolation, bus coupler operation, source transfer, and protection coordination. For Tier 4, we see additional requirements like single source or path failure tolerance, maintaining active path continuity, and preventing intertrip and cascade failures. Moving on to UPS, STS, ATS, and PDUs, Tier 3 evidence includes bypass or maintenance paths, module failure handling, load sharing autonomy, and transfer quality. Tier 4 demands more stringent fault tolerance, such as inverter faults or source faults without any load drop, and no dependence on common mode control. For generation fuel systems, Tier 3 requires testing under alternate source conditions, including generator maintenance and load bank testing. Tier 4 expect the system to handle generator, cooling, fuel, or control faults while still maintaining remaining capacity without causing overload cascades. Mechanical cooling systems at Tier 3 cover N+1 maintenance for chillers, pumps, and CRH units along with stage recovery processes. At Tier 4, systems must handle faults including sensor, controller, or network failures, and support rapid restart while ensuring temperature stability. Controls and monitoring at Tier 3 involve primary and standby server tests, point-to-point communication, alarms, and graphical interfaces. Tier 4 adds robustness with controller failover, network ring resilience, power supply backup, and server failover, all without loss of control. Finally, fire and life safety systems at Tier 3 validate cause and effect responses and integration with plant shutdown and security. Tier 4 ensures safe actions remain correct even under faults in control networks or power paths. This map essentially highlights the progressive steps in testing and commissioning that ensure higher tiers of data center resilience and operational reliability. This section focuses on the CxL0 to CxL6 Playbook, which outlines the progression from initial concept through to final commissioning. It's organized around level-by-level gates, deliverables, and engineering controls, ensuring a structured and thorough approach. Specifically, this playbook is designed to guide the testing and commissioning processes for data center mechanical, electrical, and plumbing systems, helping to maintain consistency and quality at every stage. As we move through this section, we'll explore each level in detail and understand the critical checkpoints and requirements that must be met to achieve successful project outcomes. Here we have an overview of the commissioning levels important for data center MEP testing and commissioning. The process is structured into several stages, each with a clear purpose and exit criteria to ensure quality and readiness. Starting with CxL0, the design review defines the design intent, acceptance logic controls, redundancy, test strategies, and training needs. This step closes or tracks all design comments and finalizes the commissioning plan. Next is CxL1, factory acceptance and witness testing. This stage verifies equipment performance, settings, firmware, quality, and shipping readiness. Only after reviewing and accepting factory test records and resolving any issues can we proceed. CxL2 is split into two parts: delivery and installation verification and static testing. The first confirms that equipment is delivered, installed properly, anchored, labeled, and protected. This stage results in a red tag, indicating installation is complete, but not yet ready for energization. Then, static testing involves pre-energization tests such as torque checks, insulation resistance continuity, pressure tests, and safety interlocks. After successful completion, a yellow tag indicates readiness for startup. CxL3 focuses on startup and pre-functional testing, where the vendor or installer tests individual operation, settings, and local controls, as well as points connected to the building management system. Successful completion earns a green tag, signaling readiness for functional performance testing. At CxL4, system acceptance testing evaluates overall system performance, including capacity, load handling, transfer capabilities, redundancy, alarms, and heat load tests. Passing this phase gives a blue tag, authorizing integrated systems testing. CxL5, integrated systems testing, examines integrated operation and failure modes under realistic stresses and automatic sequences. This ensures the system's resilience and readiness, resulting in a white tag to confirm acceptance. Finally, CxL6 covers transition handover and training. This level is about transferring documentation, spare parts, asset data, knowledge, procedures, and lessons learned operations, with formal acceptance and training sign-off to complete the commissioning process. Each level builds on the previous, creating a thorough, structured approach to ensure the data center systems are reliable, safe, and fully functional before going live. Let's walk through the tagging process overview as outlined in the data center MEP testing and commissioning playbook. This process uses a series of color-coded tags to track equipment status through different testing and commissioning phases. We start with the red tag at CxL2A, which indicates that equipment has been installed, anchored, and inspected. At this stage, the equipment is ready for detailed quality assurance, quality control, and static tests. Next is the yellow tag, labeled CxL2B. This tag shows that static tests are complete, and the equipment is confirmed safe and ready for startup or energization. There's also a conditional yellow tag, which is temporary and allows for a restricted temporary supply, specifically to resolve sequencing constraints. After that, we have the green tag, CxL3. This means startup and performance functional tests have been completed, and the equipment is ready to proceed to the site acceptance test, or SAT. Following that is the blue tag, CxL4, marking completion of functional and performance testing and signaling readiness for the integrated system test, or IST. Finally, the white tag, CxL5, indicates that integrated system testing is complete and the equipment is ready for transition to operational status. A critical rule throughout this process is that equipment cannot move to the next level unless the previous QA/QC or commissioning tag has been signed off and the tag status log has been properly updated. This ensures rigorous quality control and orderly progression through each commissioning phase. On this slide, we're focusing on conditional yellow tag controls, which are essentially controlled exceptions rather than shortcuts to the project schedule. These tags allow for a temporary power supply, but only under very specific conditions. First, the allowed use. Conditional yellow tags are meant strictly for situations where a temporary power source is necessary to energize a particular item for a control prerequisite activity. For example, using temporary control voltage to actuate a valve during flushing, or supplying power to a control circuit before fully energizing the system. It's important to note that this tag should never be used to partially finish installation work or to bypass any static testing. Also, full system startup, especially commissioning level 3, cannot be completed while under a conditional yellow tag. Now, let's talk about the control measures in place to ensure safety and compliance. Authorization must come in writing from both commissioning leadership and the engineering authority. There cannot be any outstanding safety deficiencies or energization risks associated with the equipment. Additionally, a safe system of work must be established, which includes a temporary power plan, clear warning signage, lockout/tagout and permit controls, and an explicit expiry condition for tag. All deviations and restrictions connected to the use of this tag must be logged in both the issue log and the tag log. Finally, and this is critical, at no point should the equipment be energized beyond the approved temporary boundary set by these controls. This ensures safety and integrity throughout the commissioning process. On this slide, we're focusing on the commissioning schedule and backward planning, which is critical for a successful data center MEP testing and commissioning process. The key idea here is to develop the schedule by working backward from the final go-live or ready-for-service date. This approach ensures all necessary milestones are clearly defined and aligned. Specifically, the schedule should include important phases such as construction milestones, equipment delivery, first energization, startup activities, system acceptance testing or high-level testing, integrated system testing, training, spare part availability, and the turnover of all documentation. Another crucial aspect is coordinating the attendance and participation of all key stakeholders, contractors, vendors, engineers of record, commissioning agents, operations teams, safety personnel, and authorities having jurisdiction to make sure everyone is present and ready when testing prerequisites are met. We also emphasize documenting lead times thoroughly. Test method statements and checklists need to be submitted early to allow sufficient time for review, comments, revisions, and final approval. The approved documents must be available before starting any test execution. For live system integration, additional lead time is required for method statements, along with formal controls for any changes or risks, ensuring everything is carefully managed and compliant. Overall, this backward planning approach keeps the commissioning process organized, efficient, and aligned across all parties, minimizing surprises, and ensuring the data center is ready and operating smoothly by the required deadline. Here, we have the issue resolution log workflow, which is a critical part of our data center MEP testing and commissioning process. The workflow begins with any stakeholder raising and recording an issue. This is important because it ensures that no concerns go unnoticed. Once an issue is logged, we classify it as either a deficiency or commissioning issue. A deficiency is a non-critical, physical, or cosmetic item that won't stop the commissioning progress, while a commissioning issue is more serious and affects safety, readiness, performance, operation, or test validity. Next, the issue is assigned an owner, a due date, and the affected level, so there's clear accountability and timeline set for resolving it. Regular review happens during weekly or even daily commissioning meetings to keep track of progress. Verification is a key step where the issue is retested, and evidence of resolution is attached to confirm it's been properly addressed. Only after the resolution is approved can the issue be closed. Additionally, it's essential to note that even issues fixed on the same day should be recorded. This helps preserve lessons learned and identify root causes for future improvements. Every entry in a log must include detailed information such as equipment ID, system location, commissioning level, reference documents or tests, impact, owner, target date, status, resolution, and retest evidence. Closure can only happen once the responsible reviewer accepts the resolution, ensuring thorough validation before moving forward. This structured process is designed to maintain quality and safety throughout commissioning. On this slide, we're diving into the structure and control rules for the test method statement and commissioning test pack, key components in our data center MEP testing and commissioning playbook. Starting with the test method statement, or TMS, it's designed to be a comprehensive document that ensures clarity and safety throughout the testing process. It begins with a front sheet capturing essential details like the project name, specific systems or equipment being tested, location, a description of the test, the author, revision number, and approvers. This sets the context and accountability right from the start. The references section links all approved drawings, specifications, statement of operations SLO, manufacturer manuals, and any previous evidence at earlier testing stages to ensure the test is based on solid and up-to-date information. The procedure itself is detailed with step-by-step actions, listing prerequisites and constraints, hold points where testing should pause for checks, and clear pass or fail criteria so everyone knows what to expect. Alongside this, the risk section highlights hazards, required permits, lockout, tagout, LOTO, processes, site access, lighting, tools, temporary works, and emergency arrangements, ensuring safety is rigorously managed. Data collection is another vital part of the TMS. It includes design data, forms, expected performance trends, calibration certificates for instruments used, and relevant screenshots to document the process thoroughly. Finally, the witnessing section defines the roles involved, signature requirements, how to handle deviations, retest rules, and photo documentation that supports transparency and accountability. Moving on to the test pack structure, this acts like a comprehensive folder that tracks quality and progress throughout commissioning. It contains a QA/QC installation checklist, installation completion certificates, and a detailed list of any deficiencies or commissioning issues discovered. It also includes the approved test methods and results for levels 2, 3, and 4, demonstrating the progression and thoroughness of testing at various stages. Completion certificates for each level close out those stages formally, while final issue log links all relevant information back to system, ensuring everything is traceable. Finally, in terms of control rules, it's crucial to submit test documentation early enough to allow meaningful review. The final approved test scripts need to be in place before any test execution begins. No testing should start without documented and approved procedures, appropriate safety controls, calibrated instruments, and well-defined acceptance criteria. For live system integration, formal change and risk approvals are mandatory, along with a detailed method statement to manage complexities and ensure safety. Overall, this framework is designed to provide clarity, safety, and rigor, ensuring commissioning activities are thorough, traceable, and consistently meet quality standards. Now, let's talk about data capture and instrumentation, which are critical components in the testing and commissioning of data center MEP systems. First, regarding instrumentation control. At the initial levels, L1 through L3 vendors and specialist contractors supply the necessary instruments along with the manufacturer test records. Moving up to levels L4 and L5, the commissioning team takes the lead in defining the quantity and precise locations for various devices such as loggers, power quality monitors, thermohygrographs, power meters, gauges, and load banks. Thermal scans also play a vital role and should cover a comprehensive range of components, including cables, terminations, switchgear internals, UPS systems, ATS or ASDS units, generators, bus bars, and mechanical or electrical panels wherever applicable. It's essential to emphasize that every instrument used for acceptance testing must come with a valid calibration certificate, which must be included in the test documentation pack. Moving on to data quality. Before starting any test, it's crucial to confirm trend setup parameters such as data points, sampling intervals, alarm captures, equipment identification, and time synchronization to ensure accuracy. During testing, capture screenshots before, during, and after each critical step to provide a clear record. Additionally, it's important to retain raw data files along with summarized graphs, rather than relying solely on narrative explanations. In failure scenarios, detailed records should be maintained, including the initiating event, the automatic system response, any operator actions taken, how long it took to stabilize the system, and the sequence used to restore normal operation. All of these measures together ensure the integrity and thoroughness of the testing process, helping us to validate system performance and reliability comprehensively. On this slide, we focus on health, safety, and energization controls during data center MEP testing and commissioning. Safety is paramount. So before every test, it's essential to follow the site's safety plan, comply with local laws, and adhere to electrical safe work practices. When dealing with energized rooms, restrict access strictly to authorized and briefed personnel to minimize risk. Utilize key safety measures such as permit-to-work systems, lockout/tagout procedures, arc flash boundaries, appropriate personal protective equipment, detailed switching schedules, and ensure clear emergency communication is in place. Temporary power setups require special attention. They must have clearly defined boundaries, proper protective devices installed, clear labeling, active supervision, and a plan for a timely removal. If at any point safety controls are compromised, prerequisites are not met, or evidence for acceptance is lacking, all testing should be immediately stopped. The slide also highlights specific areas to manage risk: electrical, mechanical, fire, controls, access, temporary works, and conducting thorough test risk assessments. By carefully controlling these elements, we maintain a safe environment throughout the commissioning process. Let's take a closer look at the reporting and records process in the data center MEP testing and commissioning playbook. Reporting is crucial at every stage to ensure transparency, traceability, and proper documentation of progress. Starting with factory acceptance testing, or FAT, after the visit, a detailed report is required that includes the agenda, methods used, results, settings, any punch list items, and photos. This ensures all factory tests are properly documented and any issues noted early. During Level 2 QA/QC, weekly reports are generated that include site walk observations, inspection static tests, tag status, and updates to the inspection release list. These reports help maintain quality assurance and control as the work progresses. For Level 3 startup, there's an increase in reporting frequency. Weekly reports are mandatory, with daily updates during intensive startup phases. Key evidence here includes vendor reports, performance functional test results, settings, and proof of BMS points, all critical to verifying operational readiness. At Level 4 SAT and HLT stages, weekly reports continue with daily updates during execution. The supporting evidence documented includes script results, load data, power quality monitoring, thermography, and trend analysis to thoroughly assess system performance under stress conditions. Level 5 integrated systems testing requires even more frequent updates with daily reports and both preliminary and final comprehensive reports. These contain scenario results, raw trend files, screenshots, issue logs, and acceptance statements, ensuring detailed tracking of system integration performance and issue resolution. Finally, at Level 6 transition, documentation focuses on training and handover completion records, including operation and maintenance manuals, system manuals, as-built, spares, warranties, and training logs. This final stage guarantees a smooth handover to operations teams with all necessary information. A strong report ties all these elements together by including safety observations, completed activities, next steps, attendees, timelines, deviations, updates to issue logs, observations, recommendations, and the acceptance status. Clear, comprehensive reporting is the backbone of successful testing and commissioning. Here, we have the commissioning meeting cadence, which outlines the different types of meetings and workshops essential throughout the data center commissioning process. Starting with the monthly commissioning focus meeting held during early design and construction phases. These sessions cover overall scope, upcoming reviews, schedule alignment, trends and issues, and planning for long lead tests. Next, the weekly commissioning meetings take place from Level 2 to Level 5. These focus on functional and integrated testing development, readiness checks, constraints, test scheduling, and identifying any blockers to sign off. Alongside, we have the weekly QA/QC walk and review, also from Level 2 to Level 5, concentrating on installation quality, first in-place inspections, workmanship, any deficiencies found, and safety concerns. During the intensive testing phases at Levels 4 and 5, daily commissioning workshops are held. These focus on planning next-day tests, resource management, switching operations, risk management, instrumentation, and addressing any immediate blockers that arise. Finally, at Level 6, the transition or go-live meeting ensures operational readiness. Topics include training, spare parts, operations and maintenance plans, asset data, punch lists, and final acceptance. It's crucial that meeting minutes clearly document owners, due dates, affected equipment, decisions needed, and dependencies. However, minutes should not replace the issue log. Both serve different but important roles in tracking progress and challenges effectively. The CxL0 Design Review Playbook focuses on establishing a solid foundation for the commissioning process. The main objective here is to thoroughly confirm the owner's project requirements along with the basis of design, the overall design intent, and key operational factors like availability targets and redundancy foundations. We also assess maintainability strategies and any operational constraints that could impact performance. A crucial part of this stage involves reviewing critical technical documents, such as single-line diagrams, mechanical schematics, controls architecture, fire interfaces, cause and effect matrices, sequences of operations, and network topology. This helps us clearly identify the commissioning scope and define important elements like the level matrix, test boundaries, temporary works, monitoring points, and load bank strategies. We also establish our high-level testing philosophy, including both the high-level testing and integrated systems testing approaches. From here, we begin developing an initial commissioning plan that outlines roles, responsibilities using RASI or RACI charts, schedules, document lists, tag strategies, and an issue log structure. We place a strong emphasis on controls aspects, paying close attention to point lists, alarm hierarchies, trend data requirements, controller failover capabilities, graphics, and clear operational sequences. As deliverables, this phase produces a baseline commissioning plan and schedule, a comprehensive set of design review comments along with a closeout tracker, and draft matrices of equipment and systems across levels 1 through 5. Additionally, we prepare draft scenarios for site acceptance testing and integrated systems testing, detailing the required instruments. A systems manual outline and training plan are also developed, alongside drafts for operations and maintenance requirements, spare parts, and asset data for computerized maintenance management system. We maintain an open risk register to track critical gaps, whether in design, access, isolation protocols, controls, or acceptance criteria, ensuring nothing is overlooked as we move forward. Here we have the CxL0 Design Review Checklist organized by discipline, which is an essential tool for ensuring that all critical design elements are thoroughly examined before moving forward. Starting with electrical, the focus areas include utility diversity, medium and low voltage topology, protection and discrimination schemes, as well as systems like UPS, static transfer switches, and automatic transfer switches. Grounding, arc flash considerations, load bank connections, and metering are also key points to review. These elements ensure electrical reliability and safety. For mechanical, attention must be given to cooling redundancy and plant staging, which are vital for maintaining system uptime. Pipework isolation, pressure relief, water treatment, and heat rejection methods are crucial for operational stability. Additionally, controls and maintainability considerations, along with a method for handling high-level tests, are reviewed to ensure mechanical systems perform as intended. When it comes to controls and network, the review looks at the building management system, energy management system, and data center infrastructure management architecture. This includes validating point lists, alarm classifications, trend intervals, master and standby configurations, network ring topologies, firewall setups, time synchronization, and graphical interfaces to guarantee robust and secure monitoring and control. Life safety focuses on fire alarm systems, suppression mechanisms, smoke extraction, dampers, plant shutdown protocols, and the integration with security and lift systems. Understanding the cause and effect relationships and ensuring the authority having jurisdiction approval path is followed is critical for compliance and safety. Operations covers access protocols, safe maintenance procedures, standard operating procedures, maintenance and emergency operating procedures, training, spare parts management, operations and maintenance practices, configuration management system asset fields, as well as warranty and defect liability periods. This ensures a facility can be operated efficiently and safely over its life cycle. Finally, the tier or rated target section emphasizes that every concurrent maintenance or fault tolerance requirement must be linked to a planned test or formal analysis to validate the system's design effectiveness. An important note is that any design comments not closed at this stage should be assigned an owner, given a risk ranking, and have their downstream test impact clearly identified. This approach helps manage outstanding issues proactively and ensures accountability throughout the project lifecycle. On this slide, we're focusing on the CxL1 factory acceptance and witness testing process, which is a crucial part of the data center MEP testing and commissioning playbook. First, the global or platform factory witness testing serves to prove the product's standard performance. This includes verifying firmware, settings, capacity, efficiency, and fault response to ensure everything functions as expected. Next, the site-specific factory witness testing involves a project team directly witnessing the equipment's configuration and performance before it even leaves the factory. This hands-on review helps catch any issues early. The factory acceptance test is backed by factory quality control test documentation. This documentation is a key piece of evidence during commissioning, confirming that the equipment met all required standards. We also have the end-of-line inspection, which is a final check before shipment. It focuses on packaged, modular, or skidded equipment to catch any defects that might have been missed earlier. The overall intent of factory testing is to thoroughly document approved settings, firmware versions, performance parameters, any alarms witnessed, shipment conditions, punch lists, and deviations. This documentation is especially valuable for long lead equipment because identifying and fixing defects early prevents delays on site, protecting the project schedule. In essence, these factory tests are about ensuring quality and performance up front, saving time and reducing risks down the line. Before starting the test, it's crucial to verify the equipment identity, including the model, serial number, rating, nameplate details, and firmware or software versions. We also need to ensure that everything conforms to the approved drawings and submittals. A thorough factory inspection should be conducted to check workmanship, enclosure condition, any accessories or spares, and the shipping configuration. Additionally, settings for protection relays, controllers, VFDs, UPS units, generators, or chillers should be reviewed as applicable. During the test itself, we focus on verifying functional operation and checking alarm responses. Performance tests should be conducted at the required load levels or specific operating points to confirm proper behavior. We also perform failure and safety shutdown tests, including interlocks, to ensure all protective measures work correctly. Meter accuracy and communication links need to be checked, and where relevant, Power quality and waveform capture should be performed to detect any anomalies. After the test is complete, any punch list items should be documented along with evidence of retests where necessary. The final test report and all signed forms must be collected and organized. Settings in the firmware library should be updated to reflect any changes made during testing. Shipping release procedures, preservation methods, lifting instructions, and site receiving checks must be handled thoroughly. Finally, any open issues discovered should be connected to the commissioning issue log to ensure nothing is overlooked moving forward. Here we are looking at the CxL2A Red Tag gate, which focuses on delivery and installation verification. The key point to understand is that a red tag signifies that installation is complete, but the equipment is not yet ready to be energized. Before moving forward, the equipment must have met all the applicable CxL1 requirements, with any factory issues either resolved or formally tracked. The equipment should be delivered and inspected thoroughly. It needs to be rigged, positioned, anchored, and handed over correctly, all according to the approved design. It's also crucial that the installation area is fully prepared, including having a level floor, proper access, adequate lighting, and no conflicting construction or contamination. Protection measures must be in place to maintain safety and quality. Documentation plays a major role here. All necessary paperwork, such as submittals, factory acceptance test or field witness test reports, rigging and installation manuals, draft operations and maintenance documents, and inspection forms must be available. Initial inspection should be completed by all relevant parties. This includes a vendor, installer, general contractor, quality assurance and quality control teams, and the commissioning authority. Major deficiencies found during these inspections must be corrected to ensure compliance. Some generic inspection points to keep in mind include verifying the nameplate and serial numbers against the schedule to ensure accuracy. The equipment must show no transit damage, and all transit bolts, wedges, and lifting eyes should be removed where applicable. We also need to confirm that the correct labels and warning signs are in place. Maintenance access is clear, sufficient clearance is provided, and room conditions meet requirements. Inside the equipment, there must be no debris or foreign materials. Additionally, cabling, glands, and strain relief should be properly prepared, with grounding and bonding installed exactly as designed. Finally, all building management system and control interface cards and accessories need to be supplied to complete the setup. This thorough verification process is critical to ensure a smooth transition into the next stages of commissioning and energization. Here we have the CxL2A Installation Acceptance Checklist, a crucial part of the data center MEP testing and commissioning playbook. This checklist ensures that every aspect of the installation meets our strict quality and safety standards before moving forward. First, under documentation, we confirm that all approved drawings, submittals, factory acceptance tests, delivery inspections, manuals, and method statements are complete and accurate. Having this paperwork in order is essential for traceability and compliance. Next, physical condition involves checking for any damage, verifying dimensions and orientation, assessing hand deadness, ensuring the base is level, and confirming vibration mounts, covers, and locks are properly installed and secure. These checks help guarantee the equipment will function correctly and safely. For location and access, we verify that clearances are adequate, maintenance can be performed safely, fire stopping is intact, housekeeping is maintained, and the equipment is properly protected. This ensures the environment supports both operation and safety requirements. When it comes to cables and pipework, the checklist covers glandings, strain reliefs, supports, cleats, bend radius compliance, torque plans, pipe supports, and proper drain and vent points. Correct installation here prevents future failures or maintenance issues. Identification is about labeling. Equipment IDs, breaker and circuit labels, warnings, safety signs, and asset data all need to be clear and accurate to support operation, maintenance, and safety protocols. Grounding checks focus on earth and bonding connections, ensuring bare metal contact is solid, confirming point-to-point continuity, and inspecting test bars. Proper grounding is critical for system safety and performance. Finally, red tag acceptance involves thorough photographic documentation, especially where covers will later hide terminations. Capturing torque marks, glands, earthing, and supports in photos provides evidence of proper installation and helps with future inspections or troubleshooting. Together, these detailed checkpoints ensure our installations meet the highest standards, minimizing risks and supporting reliable data center operations. This slide focuses on the CxL2B Yellow Tag gate, which represents a static testing and pre-energization phase in data center MEP commissioning. A yellow tag means the system is ready for startup, indicating all Level 2A inspections have been completed and the red tag has been signed off. At this stage, static tests are conducted to confirm that the installation is safe and ready to be energized or started. This includes thorough testing and identification of power, control, signal, and communications cables. Mechanical checks, such as pressure, flushing, duct leakage, cleanliness, and alignment tests, are also completed where applicable. Major issues identified up to this point must be corrected, and any remaining concerns are formally risk accepted and documented. Typical evidence of static tests includes continuity, polarity, insulation resistance, and high-voltage pressure tests, as well as low-ohm tests. Additional documentation includes torque reports, especially where double markings are required, and verification of safety interlocks, mechanical operations, covers, signage, and lock-off devices. Protection settings such as fuses, breakers, relays, and CT/VD ratios are validated, along with power meter checks. Control cables undergo point-to-point inspections and segregation checks. Finally, pre-start photographs of electrical cubicles are taken before covers are closed, providing visual proof of the system's condition at this critical stage. This thorough process ensures the system is fully prepared and safe for the next phase of commissioning. On this slide, we're focusing on the CxL3 Green Tag gate, which marks the stage of startup and pre-functional testing in the commissioning process. The green tag signifies that the system is ready for the Site Acceptance Test, or SAT. Startup is carried out by the vendors or installers following approved procedures and the manufacturer's instructions. The goal here is to ensure a safe activation of the equipment, the correct configuration of settings, individual system operation, and overall readiness for the subsequent functional testing phase. It's crucial that all critical systems are fully verified before they are presented for any witness testing. At this point, all documentation, including startup reports, configuration settings, alarms, calibration certificates, and test records must be uploaded and thoroughly reviewed. If any issues arise that could impact safety, proper operation, or the validity of tests, those need to be addressed, corrected, and retested prior to awarding the green tag. The pre-functional testing, or PFT, focuses on several key areas. Vendors perform live tests and control voltage checks, ensuring proper equipment rotation, phasing, and confirming that local and remote controls, interlocks, trips, and shutdowns operate correctly. Protection relays undergo secondary injection tests, differential and blocking checks, and breaker fail tests where applicable. We also measure flow, pressure, air volume, and system balance, while verifying valve and damper stroke, as well as variable frequency drive settings. Building and energy management system points are checked for proper graphics, alarms, trends, and communications. Finally, operational checks are conducted to confirm everything aligns perfectly with the approved sequence of operation. This thorough process ensures that systems are safe, functional, and fully ready before moving on to the final acceptance stages. This slide focuses on the CxL4 Blue Tag gate, which is all about functional and performance testing during the site acceptance testing phase. The key concept here is that the blue tag signifies the system is ready for integrated system testing, or IST. First, all systems involved are set to full operation with every component that makes up the system activated. This testing phase verifies several critical aspects: the sequence of operation, how well the system performs under various conditions, its capacity and redundancy, how it interfaces with building management systems, energy management systems, or SCADA, and how it responds to failures. Electrical load and transfer testing are conducted using the maximum available loads and load banks when necessary, ensuring the system can handle peak conditions. Similarly, mechanical load testing and heat load testing are performed to confirm the system's capacity and its ability to recover properly. It's important to note that all data gathered during these tests, including raw data, trends, power quality files, screenshots, and detailed site acceptance testing records, are included in the final commissioning report. This ensures transparency and provides a solid baseline for system performance. The testing process is tightly controlled. Scripts for testing should be coordinated by the commissioning team and carried out by the responsible contractors or vendors. Witnessing of these tests isn't just a formality. It requires the presence of the commissioning authority, as well as relevant owner, operator, and engineer of record representatives. Clear pass or fail criteria must be set ahead of time, covering key factors like timing, temperatures, transfer quality, alarms, load conditions, and manual operations. Lastly, any Level 4 issues that might impact integrated system testing must either be fully resolved or formally approved before moving forward to Level 5. This ensures a smooth transition and a robust, reliable system. Here we discuss the CxL5 White Tag Gate, which focuses on integrated systems testing, or IST. The term White Tag signifies that integrated resilience has been accepted, meaning the system's ability to withstand and recover from disruptions is confirmed. Integrated systems testing subjects the entire infrastructure, from individual plants and subsystems to complete systems and components, to simulated service stresses that mimic real operational conditions. It's crucial that these tests run in automatic mode, as intended by design, unless there's a specific need to validate manual control modes. Before finalizing the IST scripts, all scenarios, trend points, additional monitoring locations, tools like load banks or heaters, and acceptance criteria must be agreed upon. This ensures comprehensive coverage and clarity. The core purpose of IST is to validate how different elements interact: electrical systems working with mechanical components, control systems coordinating with fire and life-saving mechanisms, and how monitoring integrates with operational responses. After testing, a preliminary report indicates whether the infrastructure is recommended for acceptance, while the final report provides all raw data for detailed review. Typical test scenarios include simulating utility failures and restoration processes, managing generator operations, including startup, transfer, and overload prevention, testing uninterruptible power supply failures, assessing cooling plant issues and sensor or controller failovers, as well as verifying fire alarm and suppression interactions with cooling, security, dampers, and elevators. Maintenance modes and operator actions are also thoroughly tested. All these steps ensure that the data center infrastructure operates reliably and resiliently in real-world conditions, safeguarding critical operations. On this slide, we focus on the transition, handover, and training phase outlined in the data center MEP testing and commissioning playbook. The primary objective here is to ensure a smooth and controlled transfer of all critical facility knowledge and documentation. This includes everything from spares and settings to asset data and operating responsibilities. It's essential that the operations team fully understands the system's sequence of operation, including normal and failure modes, as well as procedures for maintenance isolation, restoration, and emergency responses. The commissioning team plays a key role by thoroughly reviewing the system's manual to confirm it is complete and easy to use. Training is another vital component and must be carefully documented. This documentation should include who attended, what content was covered, practical exercises conducted, and a competency sign-off to verify understanding. Finally, a lessons learned workshop is recommended to capture what worked well and identify areas for improvement. Regarding transition deliverables, the handover package should be comprehensive. It includes a final commissioning report, operation and maintenance manuals, system manuals, as-built drawings, schematics, and cause and effect diagrams. Additionally, spare parts, warranties, defect liability agreements, and maintenance contracts need be included. Coordination studies, as-left system settings, test data, and asset or computerized maintenance management system data are also part of the package. Training records, standard operating procedures, method of procedure, and emergency operating procedures, plus an open punch list and acceptance sign-off, complete the deliverables needed to ensure the operations team is fully prepared to take over and manage the facility effectively. Now, let's take a closer look at the handover data pack, which is a crucial component of the data center MEP testing and commissioning process. The handover package is divided into several key areas, each with specific required contents to ensure a smooth transition. First, the commissioning section must include the final commissioning report, a series of detailed reports from levels 1 through 5, raw data from SAT, HLT, and IST tests test scripts, completion certificates, and a comprehensive tag log. This ensures all testing and validation records are thoroughly documented. Next, the operations package contains essential materials such as O&M manuals, system manuals, standard operating procedures, maintenance procedures, emergency procedures, sequence of operations, cause and effect diagrams, training materials, and competency logs. These documents empower the operations team to efficiently run and maintain the systems. The design records area is equally important, housing as build drawings, updated single-line diagrams, mechanical schematics, control architecture layouts, coordination studies, and breaker settings. These records serve as a definitive reference for the installed systems. For asset and maintenance, the package includes computerized maintenance management system asset data, recommended spare parts lists, warranty information, maintenance schedules, and spare parts inventory, which are vital for long-term upkeep and reliability. Quality and closeout documentation must cover the final deficiency and issue logs, status of open and closed items, retest evidence, certificates from authorities having jurisdiction, permits and testing, adjusting, and balancing reports. These documents confirm that all quality requirements have been met and the project is properly closed out. Lastly, settings evidence contains as-left settings for everything from breakers, relays, UPS, ATS, and STS, to variable frequency drives, controllers, and building or energy management systems, alarms, and trends. This information is critical for ongoing system stability and troubleshooting. It's important to understand that the handover process is not complete until the operations team is fully equipped and confident to operate, monitor, maintain, and recover the system safely, relying on the information provided in this data pack. This comprehensive transfer of knowledge and documentation is what ensures the data center's successful long-term operation. On this slide, we outline the comprehensive training curriculum designed for operations and engineering teams, specifically focusing on data center MEP testing and commissioning. First, we start with facility orientation. This covers essential aspects like site access, safety protocols, plant room layouts, MEP system topology, and emergency evacuation routes to ensure everyone is familiar with the environment and safety measures. Next, we provide a system overview. Here, trainees gain knowledge about the electrical systems, cooling infrastructure, control mechanisms, life safety systems, monitoring tools, and the different interfaces involved in the data center's operation. The third section covers a sequence of operation, detailing how systems function under various conditions, normal, standby, maintenance modes, as well as how to respond during failures, restorations, and alarm situations. Following that is practical operation training. This includes hands-on activities such as switching operations, adjusting set points, managing controller failover, utilizing building and energy management systems, and operating local control panels. The fifth area focuses on fault diagnosis. Trainees learn first-level investigation techniques, how to interpret alarms, implement immediate recovery actions, and the proper steps for escalating issues when necessary. Maintenance isolation is another critical topic. This involves understanding methods of procedure, lockout-tagout protocols, bypass strategies, conducting risk assessments, and performing thorough return-to-service checks. We also cover emergency response procedures for scenarios like power or cooling loss, fire alarms, leaks, fuel system failures, and communication breakdowns to ensure swift and effective action during critical incidents. Finally, competency sign-off wraps up the training. This includes attendance verification, practical demonstrations, question and answer sessions, and identifying any remaining training gaps to ensure full readiness. Together, this curriculum ensures our teams are well prepared to maintain reliable and safe data center operations. This section focuses on the MEP system commissioning modules, which are crucial for ensuring that all mechanical, electrical, and plumbing systems operate efficiently and safely. We'll cover playbooks for various systems, including electrical, mechanical, controls, monitoring, and life safety. These playbooks provide detailed guidance and standardized procedures to streamline commissioning activities. Specifically, we'll look at the data center MEP testing and commissioning playbook, an essential resource for validating system performance and reliability in critical environments. Understanding these modules is key to achieving seamless integration and optimal functionality of all building systems. Here we have the equipment coverage matrix for the electrical power path, which outlines the testing and commissioning requirements across different levels for various electrical components in a data center. Looking at the matrix, the columns represent different testing levels, from L1 through L6, with specific integration focuses at L4. The rows list key equipment such as high voltage panels, transformers, medium and low voltage panels, power distribution unit switchboards, circuit breakers, generators, and their auxiliary systems like fuel and cooling. We can see that most equipment undergoes testing at levels L1, L2A/2B, and L3, with site acceptance tests or functional performance tests indicated at L4. For example, HV panels, transformers, and MV panels all require these SATs. The specific focus at L4 often includes scenarios like utility or generator failures, intertrip protection, thermal issues, and tap or soak tests. Circuit breakers are an exception, typically starting at L2 testing and focusing on settings and trip tests as part of panel testing. Generator systems not only get SATs but also load testing and evaluation of cascade failures or load sharing. At higher levels, L5 and L6, the focus is on more detailed and comprehensive testing, such as synchronization, load sharing, failure response, and transfer mechanisms, ensuring resilience and reliability under operational stresses. The legend clarifies that Y means the equipment is included for that level. SAT refers to specific acceptance tests, and not applicable indicates that testing is not normally required for that level. Of course, these are tailored to the approved design of the data center. Overall, this matrix provides a structure and detailed framework to ensure thorough testing coverage across all critical electrical power path equipment, supporting safe and reliable data center operations. This slide presents the equipment coverage matrix for electrical monitoring and ancillaries, which is a key part of our data center MEP testing and commissioning playbook. The matrix details the inclusion and testing requirements for various electrical equipment and systems across different project levels from L1 through L6. Looking at the table, Y indicates that the equipment is included at that level, while SAT refers to site acceptance or functional performance testing. Not applicable means the item is generally not required unless specified by the approved design. For example, ASDS or automatic transfer switch systems are included and tested at multiple levels, with L4 focusing specifically on synchronization, unsynchronized transfers, and failure modes. Battery monitoring and power monitoring systems are consistently included and involve monitoring interfaces to ensure seamless electrical system integration. Branch circuit monitoring and load bank connection controls are also crucial and undergo detailed site acceptance testing to verify meter mapping and load controls. Some systems, like bus bar and bus duct, require thermal and load path integrity tests, but are not usually required at higher integration levels. Important safety and control systems, such as lighting controls, emergency lighting with lux level verification, and earthing and bonding are included primarily from L2A/2B onward, with specific tests around continuity, autonomy, and functional controls. Overall, this matrix helps us understand which electrical monitoring components are essential at each stage and the corresponding testing focus to ensure robust and reliable system operation throughout the commissioning process. This structured approach ensures all critical elements are thoroughly checked and validated according to the project's design requirements. Here we have the equipment coverage matrix for mechanical and cooling systems, which outlines the different levels of testing and commissioning required across various equipment types in the data center. Looking at the table, you'll notice columns labeled from L1 through L6, each representing stages or levels of testing, from initial inclusion to system integration and final acceptance tests. For instance, air handling units and fan coil units are included in almost all levels, right from L1 up through L6, with an emphasis on site acceptance testing at L4 and BMS control integration to ensure proper building management system operations. Dehumidifiers and cooling pumps, on the other hand, start from L2A/2B, indicating they aren't involved in the earliest testing phases, while frost protection and treated RO water systems come in later and sometimes are not required at certain levels, depending on the design. Cooling towers and chillers are critical too, with testing including both site acceptance and load testing by L4, reflecting their importance in maintaining cooling capacity. The matrix also shows specific focus areas at L4 integration, such as BMS control integration, thermal response for CRAH units, and civil or mechanical acceptance checks for drainage systems. Finally, the legend clarifies a notation. Y means the equipment is included in that level of testing. SAT refers to site acceptance or functional performance tests, and not applicable indicates that a test is not normally required and should be tailored to the approved design. Overall, this matrix helps ensure that all mechanical and cooling equipment undergoes the appropriate level of scrutiny to maintain operational reliability in the data center environment. On this slide, we have the equipment coverage matrix, which focuses on controls, security, and life safety systems within the data center MEP testing and commissioning playbook. The matrix breaks down various equipment and systems across different testing levels, from L1 through L6. You'll notice that essential systems like the building management system, central management system, access control, CCTV, and fire alarm system are consistently included from L2A/2B upwards, with site acceptance testing emphasized at L4. This level typically involves thorough functional performance testing to ensure systems operate as designed in the actual environment. Integration points are critical here. For example, integrating the BMS with plant operations and alarm systems, or verifying security system through CCTV checks. Access control systems interface closely with fire alarms to maintain building safety protocols. Similarly, fire suppression systems, including water mist, sprinklers, and gas suppression, all require testing focused on their interaction with fire alarm systems and room integrity. Some systems like dry risers and communication networks have specific notes. Dry risers need authority and fire service checks, while communication networks focus on switch and fiber resilience. The notation, Y, indicate inclusion at each test level. SAT identifies where site acceptance or functional performance tests occur, and not applicable signals when testing is not normally required. Overall, this matrix helps guide the structured testing and commissioning process, ensuring every critical system is validated appropriately and integrated seamlessly for operational readiness and safety compliance. On this slide, we're focusing on the HV150 kV and MV20 kV switchgear playbook, specifically for main panels and medium voltage distribution gates. Remember, 20 kV is considered medium voltage here, while 150 kV is reserved for utility interfaces. We have a 4-tier verification and testing process, color-coded for clarity. Starting with L2A, indicated in red. This phase covers all the documentation and preliminary inspections. It includes approved single-line diagrams, protection studies and settings, as-built factory drawings, and ensures that delivery inspections and factory quality assurance checks are complete. We also verify physical aspects like nameplates, labels, anchoring, grounding, and clear cable schedules, calibration certificates, manuals, and installation checklists. Moving to L2B, the yellow level. This focuses on detailed visual and electrical inspections. Visual checks include confirming non-ferrous gland plates for single-core cables and torque mark verification. Electrical tests involve continuity, polarity, low resistance checks, insulation resistance, high voltage pressure tests, partial discharge measurements, and ensuring all secondary wiring is tight. Safety interlocks, input-output signals, CT/VD testing, and integration with automation systems like BMS, EMS, and SCADA are also validated point-to-point. In L3 marked green, the emphasis shifts toward protection logic and relay testing. This consists of verifying the latest protection logic revisions, performing secondary injections on relays, including differential, blocking, and breaker failure tests. We confirm the protection settings align with the discrimination study and are properly sealed. Accuracy of power meters is checked, alongside reviewing complete documentation and test check sheets. Finally, L4 in blue covers full load testing and system integration. Tests are conducted at the maximum available load, and all interlocks and transfers involving utility, generators, and bus couplers are exercised. The SCADA system is tested for manual and automatic breaker control, as well as alarm and status visualization. This level also includes system responses for utility failures, maintenance conditions, breaker failures, communication losses, DC source failures, and thermal scans. Together, these layers ensure that the switchgear system is thoroughly tested, fully documented, and ready for reliable operation. On this slide, we are focusing on the transformer playbook, specifically for oil-filled and cast resin transformers, which is a critical part of the data center MEP testing and commissioning playbook. The process is divided into 4 key levels, each associated with a color code that helps organize and prioritize the tasks. Starting with level 2A, marked in red, this stage is all about ensuring the transformers arrive in perfect condition. We carefully review transport and vibration records and perform a thorough visual inspection alongside factory QA and QC. We verify the correct type and rating, check nameplates, serial numbers, warning labels, and ensure all dimensions and orientations are accurate. Important details like glanding, strain relief, grounding, and the condition of BMS or temperature interface cards are checked as well. The location must be ready, free of debris, and any transit bolts or wedges must be removed. Moving to level 2B, indicated by yellow, the focus shifts to functional and electrical checks. This includes testing tap changer operation both locally and remotely if applicable. Torque and earth bonding must be inspected, with attention to bare metal contacts. We verify ratio and vector groups, conduct CT tests, and perform insulation resistance tests before and after dielectric and pressure testing. Thermistors, thermal relays, and trips and all control and signal points are confirmed to be operating correctly on a point-to-point basis. Level 3, represented by green, emphasizes continuous monitoring and prolonged testing. Key alarm and trip points related to temperature, pressure, and bookhold devices are verified. Integration with switchgear and protection panels is confirmed through inter-trip and interlock checks. The transformer undergoes a 24-hour no-load soak, with automatic cooling systems and tap voltage checks performed during this period. Where applicable, oil samples are taken for analysis, alongside sweep frequency response analysis, voltage ratio measurements, and winding resistance checks. Finally, level 4, denoted by blue, is about putting the transformer under full operational conditions. A loaded soak test is conducted along with verification of cooling fans where fitted. Load testing uses approved downstream loads when permitted. Sound and vibration assessments are carried out as required. Final fire stopping measures are completed, and the process concludes with fault and snag-free handover, ready for full system integration. Together, these levels ensure that transformers are tested thoroughly at every stage, from delivery through to full commissioning, supporting reliable and efficient data center operations. On this slide, we're diving into the generator's NER and SCADA playbook, which is a critical part of emergency power generation and power control integration for data center MEP testing and commissioning. Starting with level 2A, marked in red, we ensure the generator is positioned exactly as per the shop drawings and the alternator class is verified. It's important to have all factory test documentation, as-built drawings, and the pre-commissioning checklist ready. We also confirm proper earth connections, labeling, interface and cable schedules, and calibration certificates. Additionally, the generator must be free from any transit damage, with the correct dimensions and orientation, and have the building management system interface applied as specified. Moving to level 2B, indicated in yellow, this stage covers detailed point-to-point verification of generator I/O and fuel alarm points. We verify the controller firmware and settings, check cable torque, insulation resistance, and pressure test certificates. Protective devices and time delays must match the approved settings to ensure reliable operation. At level 3, signified by green, the focus shifts to the first startup and safety checks. We perform operation checks and controlled shutdowns. This includes verifying phasing, battery, and charge performance, fail-to-crank scenarios, and testing fire alarms and alarm/shutdown functions. Instrumentation accuracy and load sharing are tested, alongside interfaces to monitoring systems and the network equipment room. SCADA and PLC input-output, as well as local and remote control functions, are thoroughly verified here. Finally, level 4, shown in blue, centers on load sharing and metering during both normal and failure scenarios. We simulate building utility failures, generator cascade operations, system redundancy, and NER control and failure modes. Utility failures during retransfer and utility blip tests are also tested. Continuous monitoring using SCADA and energy management systems, routine maintenance scenarios, and thermal scans are completed to ensure ongoing reliability and efficiency. This structured approach guarantees that every aspect of emergency power generation and control integration is rigorously tested and commissioned for seamless operation in critical environments like data centers. Here we focus on the comprehensive testing and commissioning procedures for HV150 kV, MV20 kV, LV, control, instrument, and ICT cables within the data center infrastructure. Starting with cabling, it's essential to ensure proper routing, support, and spacing to maintain system integrity. We verify that cleats are correctly installed, segregation is maintained to prevent interference, and bend radii are within acceptable limits. All cables must be clearly labeled. Glands need to be sealed properly to preserve enclosure ratings, and strain relief must be provided to avoid mechanical stress. Testing includes insulation resistance, pressure testing for ducts, continuity checks, polarity verification, point-to-point confirmation, and torque mark inspections. Additionally, photographing concealed terminations prior to closure helps document the quality of the installation. Moving to bus duct and bus bar systems, the focus is on ensuring the correct routing and support so that joints are properly aligned and tightened with the specified torque. Covers must be securely in place. Insulation resistance and continuity tests are performed thoroughly. Joint inspection under load, including thermal scanning, is done to detect any issues. Tap-off units are checked along with labels and interlocks to guarantee operational safety and reliability. Next, earthing and bonding systems need careful attention. Earth bars, bonding jumpers, equipment earth connections, and cable screens must have bare metal contact supported by anti-loosening hardware. Torque marks provide evidence of proper installation. Point-to-point continuity and resistance tests confirm electrical integrity. Labels and test points should be accessible for maintenance and verification. Finally, lightning protection involves air terminals, down conductors, bonding, and earth pits to safely dissipate any lightning strikes. Continuity and earth resistance testing are critical, along with documentation of surge protection interfaces and labels. Compliance with the authority having jurisdiction and local standards is vital to ensure overall safety and regulatory adherence. These detailed checks and documentation form the backbone of a robust, safe, and reliable data center MEP system. This slide outlines a UPS, STS, ATS, and ASTS playbook focused on critical power continuity and transfer quality within data center MEP testing and commissioning. Starting with level 2A and 2B checks, we verify equipment identity against factory records and conduct dead test methods. We inspect AC and DC supply and load cables, control signals, labeling, torque settings, and insulation resistance. Battery strings and external DC controls are reviewed, along with earthing systems and emergency power-off or interlock circuits. It's essential that the startup method statement is fully approved before proceeding. Moving on to level 3, marked in green, this stage involves live vendor testing based on the approved methods. Critical elements include verifying interlocking mechanisms, Castell key functionality, UPS to STS transitions, including bypass and return sequences, load sharing, and module communications. We also evaluate BMS and EMS alarms, confirm settings, and review calibration certificates to ensure accuracy. At level 4 for the UPS itself, testing involves subjecting the system to loads at 25, 50, 75, and 100% capacity, followed by a 4-hour heat run at full rating to assess durability. Full load transfer tests are conducted with power quality monitoring on both input and output sides. Battery autonomy is checked through discharge testing, alongside static and maintenance bypass functionality. We also simulate transient load steps, overload transfers, unbalanced loads, and utilize thermal imaging to detect any hot spots or issues. For level 4 testing of ATS and ASTS systems, we test normal and emergency source failures and returns. Both synchronized and unsynchronized transfers are evaluated, with ASTS specifically holding the same source during inverter failure to maintain power stability. Maintenance bypasses and interlocks are verified, and we carefully monitor transfer timings, waveform integrity, alarm functions, meter accuracy, and overall BMS and EMS system status. Overall, This playbook ensures comprehensive testing to guarantee reliable power continuity and quality transfer across critical data center power infrastructure. Here we focus on the critical components involved in low-voltage distribution, metering, and branch circuit observability within data center infrastructure, starting with switchboards and battery transfer units. Testing is comprehensive, covering protection settings, breaker operation, interlocks, meter verification, and various electrical tests like infrared scans and torque checks. We also verify proper functioning of mains failure response and generator transfers, while thermal scans ensure components operate safely under full load conditions. Moving to power distribution units and remote power panels, the key checks include confirming correct panel specifications, breaker counts and ratings, and accurate circuit labeling. Input and output cables are inspected thoroughly, along with torque, insulation resistance, phase rotation, and earth bonding. For PDUs with automatic transfer switches, transfer tests and source loss tests are conducted to guarantee reliability. Additionally, we validate metering and branch circuit data to ensure accurate energy monitoring. In battery cell monitoring, attention is given to current transformer orientation, precise circuit mapping, and communication setup, including Modbus addressing and gateway configurations. We ensure that the panel layout is installed matches the monitoring registers and prepare asset data well in advance of operational handover to avoid surprises. Finally, for battery monitoring, we assess string and cell sensors for proper polarity, communication integrity, and alarm functionality. Threshold settings along with resistance, temperature, and voltage readings are closely monitored. Integration with UPS and energy management systems is verified, and alarm graphics are checked for clarity. This phase also includes calibration, baseline reporting, and operator maintenance training to ensure ongoing reliability and safety. Overall, this thorough testing and verification process is essential to maintaining robust, resilient power distribution and monitoring systems within the data center environment. Here we have a generic AIB critical power distribution schematic designed specifically for data center MEP testing and commissioning. The key concept here is the clean separation between the power flow and the monitoring or alarm telemetry systems. On both sides, Utility A and Utility B provide the high voltage power input at 150 kilovolts, which then steps down through medium voltage switchgear and transformers to low voltage switchgear. From there, uninterruptible power supplies feed the power distribution units, ultimately supplying the IT loads. This dual A-B path ensures redundancy and reliability, allowing continuous operation even if one side experiences a failure. In addition, a generator setup with an N+X configuration provides backup power to maintain uptime during utility outages. The bus coupler plays an important role in connecting these paths and managing power flow, while various monitoring platforms like EPMS, BMS, and DCM track trends, events, and alarms in real time. The legend helps distinguish power paths from monitoring and alarm telemetry, emphasizing the importance of both for system reliability. Crucial proof points from SAT and IST tests include high and medium voltage source loss detection, generator start and load sharing behavior, bus coupler interlock functionality, UPS ride-through capability, transfer switch timing, protection coordination, and the accurate reporting of events and alarms by monitoring systems. Together, these elements form a comprehensive framework that supports a secure and reliable power distribution essential for data center operations. Now, let's focus on Section D, which covers the integrated extended equipment commissioning. This section outlines a comprehensive scope for commissioning multiple critical systems, including mechanical, electrical, and plumbing systems, as well as fire safety, security, logistics, and containerized plant operations. All these elements are integrated to provide a cohesive technical playbook, ensuring that every piece of equipment is thoroughly tested and commissioned in a streamlined, efficient manner. This approach helps us maintain consistency and reliability across all the interconnected systems. Here we have the integrated scope map from the MEP testing and commissioning playbook. This map outlines a comprehensive commissioning scope, along with evidence requirements broken down by discipline. Starting with electrical coverage, it includes high-voltage systems like the 150 kV utility interface and cables, medium-voltage distribution at 20 kV with switchgear and cables, and low-voltage components such as bus ducts, control cables, and transformers of various types, cast resin, oil-filled, and isolating. Next, power conversion and storage covers commissioning of lithium and VRLA batteries, battery monitoring systems, uninterruptible power supplies, static and automatic transfer switches, power distribution units, and load bank tests for both air and water-cooled systems. Under platforms and controls, the focus is on verification of EPMS, CPOS, and DCIM systems, along with their operational technology network interfaces. This includes evidence generation for timestamps, alarms, trends, dashboards, and ensuring cybersecure handling of commissioning data. For fire and leakage systems, the scope distinguishes between water and fuel leak detection. It covers fire hydrants, brigade inlets, city water outlets, fire pumps, and advanced smoke detection and suppression technologies, all integrated with cause and effect logic. Additionally, compliance with standards like SNI, NFPA, and local authority having jurisdiction witness requirements is emphasized. Security and logistics address perimeter and access controls, such as fences, gates, road blockers, crash-rated entries, turnstiles, and screening devices including X-ray and man-traps. Loading dock equipment is also included for safety and logistic support, as well as use of overhead cranes for equipment installation. Lastly, containerized plants cover commissioning of modular container units housing medium-voltage switchgear, transformers, control and power distribution systems, generators, fuel systems, and load banks. The overall result is a detailed commissioning playbook that provides extensive coverage and includes a corrected Level 1 and factory acceptance test matrix tailored to major factory-tested systems, ensuring quality and consistency throughout the commissioning process. On this slide, we're focusing on the importance of using consistent voltage terminology throughout all MEP testing and commissioning documentation and communication, starting with the key voltage levels. High voltage, or HV, refers to the 150 kilovolt utility incomers, while medium voltage, or MV, corresponds to the 20 kilovolt feeders and RMUs. It's critical to never mislabel 20 kV cables as HV in commissioning records, as that can lead confusion and safety risks. Low voltage, or LV, begins downstream of the transformers. The slide also highlights the typical utility interface, showing flow from the 150 kV HV utility interface through the step-down transformer to 20 kV MV reticulation, then to MV switchgear like RMUs and feeders, and finally down to LV critical distribution. From a terminology rule perspective, the takeaway is to strictly differentiate HV and MV components and ensure all test packs, tags, drawings, training, and defect logs reflect this consistently. In terms of commissioning consequences, this clear distinction means that we apply different test methods for HV and MV systems, align test voltages with voltage classes, confirm switching authority and permits before work, and clearly tag energization boundaries for safety and clarity. Finally, regarding tier or rating implications, maintaining dual paths must allow for proper maintenance without cascading faults. Monitoring must reliably verify the health of these paths, and single event responses should be validated during the integrated system testing phase. Overall, clear and consistent use of voltage terminology is crucial for safety, efficiency, and effective commissioning of electrical systems. Here we have the expanded CxL1 factory acceptance testing, or FAT, scope, now applied explicitly to major equipment packages that come with factory-configured logic. This means that for each key piece of equipment, specific tests and evidence are required before it leaves the factory. For transformers, whether dry, cast resin, oil-filled, or isolating types, the focus is on routine and special factory tests, along with verifying nameplates, accessories, and protection interfaces. The evidence includes detailed FAT reports, test certificates, drawings, a transport plan, and an accessory checklist. In the case of power distribution units and low-voltage distribution packages, testing centers on protection functions, metering accuracy, building management communication, interlocks, labeling, wiring, and configuration. Required documents include FAT checklists, metering maps, breaker settings, and a serial number register. Generator sets and containerized gensets undergo tests on engine and alternator performance, controller logic, safety shutdown sequences, and load step behavior. The factory load run report, controller settings, and battery and charger records serve as proof. For generator fuel systems and fuel polishing units, components such as tanks, pumps, PLC controls, filtration, leak alarms, and fuel quality monitoring are tested functionally in the factory. Evidence here involves functional test reports, input-output lists, and filter and sensor certificates. Uninterruptible power supplies, UPS, static transfer switches, STS, and automatic static transfer switches, ASTS, are assessed on power conversion efficiency, transfer logic, bypass functionality, interlocks, and waveform or power quality. Supporting evidence includes FAT plots, settings, battery interface records, and event logs. Lithium and valve-regulated lead-acid batteries, along with their monitoring systems, require quality assurance on cells and strings, logic validation for battery management systems, and verification of alarms and communication protocols. Data such as cell performance, baseline impedance or conductance, and alarm test records are collected. Chillers and computer room air handling units undergo factory performance testing and controls calibration, sensor validation, alarm testing, and communication checks. The evidence includes factory performance sheets, controller settings, and sensor calibration certificates. Finally, containerized electrical plant are validated for integrated container services, including fire protection, HVAC controls, ACMP or PLC HMI systems, communications, and safety features. The factory acceptance process results in an integrated FAT and site integration test dossier, punch list closures, and configuration freeze documentation. This structured approach to CxL1 FAT ensures that major systems are thoroughly verified with clearly documented evidence, reducing risks and ensuring seamless integration on site. Here we have the Master Integrated Commissioning Scope Matrix, an essential guide for engineers focusing on integrated systems during planning and witnessing phases. It breaks down the scope groups by system type, each with its primary commissioning emphasis. Starting with HV/MV power systems. This involves high voltage interfaces and medium voltage switchgear. The key checks here are permits, protection mechanisms, cable testing, proper route segregation, and ensuring switching safety. For transformers, whether dry, oil-filled, or isolating types, the focus is on factory testing, verifying insulation conditions, protection settings, thermal soak monitoring, and inter-trip functionalities. Energy storage systems like lithium and VRLA batteries require attention to safety logic, autonomy settings, alarm functions, baseline performance data, and monitoring for thermal conditions or hydrogen buildup. In the distribution category, which covers bus ducts and low-voltage control and instrument cables, it's critical to verify route integrity, torque of connections, insulation resistance and continuity tests, proper labeling, and resilience of bandwidth or operational technology. Fuel and load systems include fuel polishing, leak detection, and load banks cooled by air or water. The commissioning emphasizes validating fuel quality, isolation mechanisms, heat rejection processes, load step operations, and generator demand controls. Platform systems such as EPMS, CPOS, DCIM, and OT networks require detailed point mapping, trend analysis, accurate timestamps, control response checks, and event correlation. Fire water systems encompass hydrants, fire brigade inlets and outlets, pumps, and detection systems like ASD or VESTA. The priorities are flow and pressure verification, alarm supervision, authority having jurisdiction witness, and cause and effect proofing. Lastly, security and logistics systems cover perimeter security, loading docks, overhead traveling cranes, elevators, and building maintenance units. Here, the focus is on safety interlocks, fire release mechanisms, operator training, and maintenance access. Altogether, this matrix ensures that each integrated system receives thorough commissioning attention tailored to its unique requirements, leading to safer and more reliable operation. Here we have the Integrated Commissioning Item Register, specifically for electrical power and cables. This is a crucial part of our data center MEP testing and commissioning playbook. The register maps the source commissioning item list directly into the electrical commissioning section, ensuring nothing is overlooked. On this table, You can see different electrical assets along with their quantities and the corresponding commissioning levels assigned from the source list. For example, MB switchgear requires thorough testing across multiple levels, from CxL1 through CxL5, supported by factory acceptance tests and material inspections on site. Other critical equipment like transformers, PTUs, and gensets also have defined commissioning tasks, including visual inspections and documentation checks to verify certification. Power distribution components, such as bus ducts and switchboards, undergo a combination of visual inspection, technical parameter checks, and factory witness tests where applicable. It's important to note the systematic approach here. Each asset is tagged with test packs, evidence owners, witness levels, and defined paths to resolve any issues found. This ensures a structured, controlled process that supports comprehensive verification and accountability throughout commissioning. Using this register as a planning control tool helps us maintain consistency and traceability, which is vital for the reliability and safety of the data center's electrical systems. Here we have the integrated commissioning item register, focused on electrical power and cables, part 2 of this segment. This register is a crucial tool in our data center MEP testing and commissioning playbook. It helps us confirm the ownership within the test management system, verify the required witness levels, and track evidence records for each asset. Looking at the table, you can see various assets listed, such as LV and MV power cables, power distribution boards, lighting control systems, power sockets, and water leak detection systems. Each asset is assigned specific commissioning levels, ranging from CxL2 up to CxL5, depending on complexity and criticality of the component. For example, power distribution boards require the highest level of commissioning, including level 5, while power sockets primarily require levels 2 and 3. The representative tasks for each asset involve visual inspection and technical parameter checks to ensure everything is installed and functioning correctly. For lighting control systems, there's an added layer of verification involving component installation like KNX and Dolly, as well as functional testing of individual devices. Importantly, this register isn't just for tracking. It acts as a planning control. Every asset must have a clear tag, an associated test pack, a designated evidence owner, a defined witness level, and a process for closing out any issues. This ensures accountability and thoroughness across the commissioning process, helping us maintain quality and safety standards throughout the project. This slide focuses on the testing and commissioning process for the high-voltage 150 kV cable and utility interface. The main objective here is to ensure that the high-voltage utility interface is completely safe, maintainable, and ready for controlled energization. Starting with the scope, it includes the 150 kV gas-insulated switchgear and air-insulated switchgear interface, the cable route, terminations, joints, and sheath bonding. It also covered protection systems, metering, and utility interface signals, as well as relevant permits, switching plans, and emergency restoration plans. Next, the level gate proof outlines specific stages of verification. At level 0, we review utility criteria, single-line diagrams, protection, and earthing. Level 1 involves factory routine tests for equipment and cables. Level 2A focuses on the physical installation, including route supports, labeling, and joint bays. Level 2B covers electrical tests, such as sheath testing, insulation resistance, very low frequency, high potential, and partial discharge tests as specified. Levels 3 and 4 involve energization, protection, metering, and interlocks, while Level 5 verifies utility loss, return, and maintainability scenarios. For acceptance evidence, it's critical to have approved switching programs and isolation certificates, detailed cable test reports using calibrated instruments, document protection settings including relay injection and trip matrices, as-built route records with thermal baseline data and photos, and EPMS alarm timestamps to confirm operational readiness. Finally, a common trap to avoid is mixing test records for the HV 150 kV and medium voltage 20 kV systems. Each voltage class requires its own permits and acceptance criteria, so keeping these separate is essential for compliance and safety. On this slide, we're focusing on the medium voltage 20 kV cable reticulation and switchgear commissioning. The key objective here is to confirm that the entire 20 kV distribution path can be safely operated, isolated, transferred, and maintained without any hidden defects that could cause issues down the line. Starting with the commissioning scope, it covers everything from the MV switchgear and ring main units to feeders, cable terminations, and current and voltage transformers. We also look at relay and protection settings, ensuring that tripping and interlocks function correctly. Additionally, the DC trip supply, chargers, alarms, and arc flash interfaces are tested. The scope further includes physical protection such as fire stops, segregation, and mechanical safeguards along the MV route. Moving to the level gate proof, this is a step-by-step checklist that guides the commissioning process. Level 0 ensures key designs like single-line diagrams, coordination studies, arc flash analysis, cable sizing, and switching operation orders are all in place. Level 1 includes factory acceptance testing of switchgear and RMUs, relay simulations, and checks on current and voltage transformers. Level 2A verifies installation quality, labeling, earthing, and clearance access. Level 2B focuses on torque settings, electrical continuity, insulation resistance, and advanced cable testing like VLF or HiPOT, plus secondary wiring verifications. Level 3 covers relay injection tests, breaker operations, and DC supply tests. Finally, Levels 4 and 5 validate source transfer procedures, feeder fault handling, and maintenance isolation protocols. For acceptance evidence, it's crucial to have a complete test pack for MV cables and switchgear. This includes relay setting files, injection test reports, seal records, torque and insulation resistance certificates, and evidence from the electrical power monitoring system covering point-to-point checks and alarm events. Formal approvals for switching, lockout, tagout, and energization must also be documented. A common trap to be cautious of is correctly labeling all 20 kV systems in drawings, checklists, method statements, and tags. Mislabeling can cause confusion and errors during commissioning and maintenance, so consistency here is key. Overall, this playbook segment ensures that the 20 kV electrical distribution system is fully verified and ready for safe operation without surprises. This slide covers the testing and commissioning process for bus duct and bus bar trunking systems, which are critical for ensuring high current electrical distribution routes are safe and reliable. Our main objective here is to verify that these bus bar routes are mechanically complete, electrically continuous, and thermally stable when carrying load. The commissioning scope includes inspecting main bus ducts, riser bus bars, tap-off units, and end feeds. We also check joint packs, torque windows, cover supports, fire barriers, earthing and bonding, as well as phase sequence. It's important to ensure proper integration with transformers, main switchboards, power distribution units, and monitoring systems. To guide this process, we follow a series of level gates. At level 0, we review the layout, fault rating, derating factors, expansion, and coordination requirements. Level 1 involves reviewing factory routine tests and type test compliance. Levels 2A and 2B cover physical installation checks like routing, supports, clearances, labeling, joint torque verification, insulation resistance, continuity, polarity, and phase sequence. Level 3 involves energizing the system under control load, and Level 4 consists of thermal scanning at progressive load steps to confirm thermal stability. For acceptance, we need documented evidence including joint torque registers with witness hold points, insulation resistance and continuity certificates, tap-off schedules with labeling photos, thermal images at accepted load, and closure of any snags related to covers, supports, and fire stopping. One common trap to avoid is closing covers that are inaccessible before obtaining witness photographs and confirming torque marks are acceptable. This ensures no issues are hidden and the installation can be confidently signed off. On this slide, we focus on the testing and commissioning of LV, control, instrument, and ICT cables, emphasizing the need to separate these tests so that the evidence aligns clearly with their specific function and associated risks. Starting with the commissioning scope, it covers several key cable types: low voltage feeders, submains, finals, and load bank camlocks for power distribution, control cables that handle interlocks, permissives, and emergency power off signals, instrument cables, including shielded twisted pair RS for 85 and Ethernet, which connects sensors, meters, and point data systems, and ICT cables, which comprise single-mode and multimode fiber optics, as well as shielded twisted pair copper cables. The level gate proof process is structured into multiple stages to ensure thorough verification. L0 focuses on documentation, such as cable schedules, routing plans, segregation, and earthing philosophies. At L1, we verify factory cable certifications and conduct factory acceptance tests of network equipment, where applicable. L2A inspects physical installation aspects, including routes, tray or ladder fill, bend radius, labeling, and fire stopping. L2B involves electrical tests, insulation resistance and continuity for power cables, and point-to-point verification for control cables. Level 3 then moves into live loop checks, signal scaling, and confirming network links. Finally, L4 and L5 consist of end-to-end functional testing, failover scenarios, and timestamp accuracy validations. For acceptance evidence, we collect detailed test sheets categorized by cable type, fiber optic test results like OTDR and light source measurements, copper cable certification reports, point-to-point test sheets, instrument calibration certificates, network topology maps, switch configurations along with redundancy tests, and the as-built cable schedule complete with redline markups for any changes. A common pitfall to avoid is accepting a single combined cable certificate as proof for all cable types. Each cable must be tested and accepted individually based on its specific function and risk profile to ensure compliance and operational integrity. Let's take a closer look at the commissioning process for oil-filled transformers. The primary objective here is to ensure that these transformers are safe, clean, properly protected, correctly connected, and thermally stable. This is critical to guarantee reliable operation and prevent any potential failures. The scope of commissioning covers several key components. We focus on the power transformer itself, including the tap changer, bushings, and all related accessories. We also verify the oil containment system, including the bund and drain valve controls, as well as oil leak monitoring. Essential protection devices such as the Buchholz relay, pressure relief valves, and temperature controls for windings, oil, and fans are thoroughly tested. Additionally, the integration with fire detection systems, EPMS and BMS alarms, and inter-trip functions to the switchgear are confirmed to work perfectly. The commissioning is organized into level gates, which help structure the process and ensure comprehensive testing. At level 0, we confirm the transformer's rating, impedance, vector group, protection, and containment. Level 1 covers factory routine tests and accessory test records. At level 2A, we verify transport vibrations, installation integrity, grounding, and condition the oil. Level 2B involves more detailed electrical tests like ratio and vector group confirmation, winding resistance, insulation resistance, and polarization index, along with further oil tests. Level 3 is about energizing the transformer, monitoring no-load soak conditions, alarms, trips, and cooling systems. Finally, Levels 4 and 5 focus on load soak testing, inter-trip operations, and thermal response verification. Acceptance evidence is a crucial part of this playbook. It includes factory test certificates and nameplate verification, detailed oil sample records assessing breakdown voltage, moisture content, and dissolved gas analysis as specified. Functional test sheets for protection and accessories are reviewed alongside thermal images and soak test trends under no-load and load conditions. All this data is compiled in a dedicated oil transformer test and maintenance schedule maintained as a separate document. One common pitfall to watch out for is confusing oil leak detection with water leak detection. These are handled by entirely separate systems, each using different sensors, alarm logic, and response procedures. It's important to treat them independently to avoid false alarms or miss critical issues. Overall, this structured approach ensures that oil transformers are commissioned thoroughly and reliably, supporting safe and efficient operation in the field. This slide summarizes the commissioning process for cast resin or dry-type transformers. The main objective here is to ensure that these transformers are clean, free of damage, properly ventilated, protected, and stable when energized under load. The commissioning scope covers several critical components. First, we verify the cast resin windings, the core, the enclosure, and the bus or cable interfaces. We also inspect the fans, temperature sensors, thermistors, RTDs, and thermal relays to confirm they're functioning correctly. Additionally, we assess room ventilation, clearances, filters, and a cleaning regimen to maintain optimal conditions. Finally, We check EPMS and BMS alarms and verify upstream and downstream inter-trip mechanisms to ensure safe operation. The commissioning process is organized into multiple level gates. Level 0 focuses on basic rating, impedance, losses, vector group, and ventilation checks. Level 1 includes factory routine tests and any partial discharge testing where specified, along with accessory records. In levels 2A and B, inspections during shipping for cracks and cleanliness, infrared and polarization index tests, ratio and vector verification, winding resistance, and control wiring are all completed. Level 3 involves energize and transformer, conducting no-load soak tests, and verify alarms and trips. The final levels, 4 and 5, focus on load soak tests, thermal scans, and simulating transfer and failure scenarios to confirm stability under real operating conditions. For acceptance, it's essential to provide evidence such as factory test certificates, accessory checklists, photos of cleanliness and resin condition, test sheets for insulation resistance and winding resistance, temperature trend data, alarm and trip logs, as well as thermal images. All this documentation is compiled into a dedicated dry transformer test management system document. Common pitfalls that many encounter during commissioning include dust contamination, blocked airflow, incorrect mapping of sensors, and incomplete proof of thermal inter-trip functions. Addressing these traps early is critical to a successful dry transformer commissioning. On this slide, we focus on isolating transformer commissioning, which is crucial for protecting sensitive loads. The main objective here is to verify proper isolation, ensure the correct earthing reference, confirm shielding effectiveness, and check downstream protections. The commissioning scope includes several key components. We look at the isolation transformer itself, including the electrostatic shield and how the neutral and earth are arranged. It's also important to confirm proper segregation of input and output cables, as well as dedicated bonding connections. Protection devices, monitoring systems, and thermal devices downstream are evaluated too, along with critical loads or control power circuits they serve. The process is structured into level gates, which help us systematically validate each step. Starting with L0, we verify isolation functions, earthing, fault studies, and harmonics. L1 covers factory testing and proving winding and shield continuity. L2A checks installation details like placement, ventilation, nameplates, and bonding, while L2B confirms insulation resistance, ratios, polarity, shield continuity, and grounding. At L3, energization tests are done, including no-load current and voltage balance, alongside alarm verification. Finally, L4 and L5 focus on load response, fault simulation when safe, and ongoing monitoring. Acceptance evidence includes factory certificates, approved earthing drawings, test reports on shielding, bonding, and insulation, as well as voltage and load trends under realistic conditions. Thermal scans help detect hot spots, and noise or vibration observations reveal mechanical issues. Updated as-built documents and maintenance instructions complete the package for handover. A common trap to watch out for is assuming the earthing reference based solely on the transformer type. The approved earthing reference is the most critical acceptance item and must be verified to avoid potential problems down the line. This slide covers a commissioning process for a lithium battery system, focusing on ensuring safety, monitoring, isolation, and integration with UPS and fire control systems. The objective here is to verify that the energy storage system operates reliably and safely within the overall infrastructure. First, the scope of commissioning includes key components such as battery racks and modules, the battery management system or BMS, DC protection devices, and disconnects. It also involves thermal monitoring to prevent overheating, ventilation, or purging if needed, and alarm systems for early warnings. Importantly, the system must interface properly with fire detection and suppression mechanisms, including emergency isolation protocols. Additionally, the UPS charger and inverter integration is tested, along with calculations to confirm the system's autonomy. Commissioning is performed in several level gates. At level 0, the focus is on autonomy, battery end-of-life considerations, thermal runaway prevention, and overall safety strategies. Level 1 covers quality assurance of cells and modules, factory acceptance tests of the BMS, and communication protocol verifications. The second level includes installation checks such as clearances, polarity verification, grounding, and labeling. Further, electrical tests like DC insulation resistance and torque checks, BMS address mapping, and alarm wiring are performed. Level 3 ensures controlled charge and discharge cycles, alarm responses, and state of charge and health data accuracy. The final levels, 4 and 5, verify UPS transfer functions, autonomy under load, emergency power off and fire interlocks, and thorough data logging. Acceptance evidence is critical and includes records such as serial registers and baseline data of cells and modules, BMS alarm logs, firmware versions, and communication maps. Settings for DC protection are documented alongside torque and insulation resistance measurements. UPS autonomy and discharge trends are analyzed in combination with thermal profiles, while cause and effect records for fire and emergency power-off events are maintained. A common trap to avoid is treating safety logic and monitoring data as vendor-only black boxes. This data and these controls must be part of the commissioning deliverables to ensure transparency, safety, and reliable operation of the lithium battery system. This slide covers a commissioning process for VRLA battery systems, which is crucial to ensure these batteries can reliably provide standby power. The main objective here is to verify that the VRLA batteries deliver the required autonomy safely and establish a solid baseline for ongoing operations. The scope of commissioning includes all VRLA cells and blocks, the racks housing them, chargers, and DC distribution components. It also covers 110 VDC trip batteries and various UPS or string applications. Where applicable, temperature, ventilation, and hydrogen monitoring systems are checked to ensure safe conditions. Additionally, the battery monitoring systems, alarms, and maintenance bypass interfaces are all part of the scope. Moving on to the level gate proof steps. The commissioning process is broken down into several stages. Initially, autonomy, charger sizing, ventilation, and replacement strategy are confirmed at level 0. Factory quality assurance of cells and blocks, along with charger factory acceptance testing, happens at level 1. Level 2 is split into 2 parts. Verifying a rack setup, including seismic anchoring, polarity, and ventilation, and checking torque, polarity, float voltage, insulation resistance, and continuity. Level 3 focuses on testing charger operation, alarm functions, ripple, and establishing baseline readings. Finally, levels 4 and 5 confirm discharge autonomy performance, checking for DC failures and critical trip functionality. For acceptance, evidence must include detailed records like the cell and block register, with baseline voltage and impedance, charger settings along with alarms and ripple test results. Discharge and autonomy curves along with thermal observations support the performance evaluation. If hydrogen or ventilation alarms are installed, their functionality must be verified with evidence. A maintenance and replacement schedule should also be in place to support ongoing battery health. A key warning to remember is to never accept battery systems without baseline data. This baseline is essential because it allows operations to detect any battery degradation early, ensuring reliability and preventing unexpected failures down the line. Let's dive into the battery monitoring system commissioning process. The main objective here is to ensure that the health data from each cell or string is not only accurate, but also properly alarmed, trended over time, and usable by the operations team. This involves verifying several key components, including battery monitor modules, current sensors, and temperature probes. We also need to confirm that the gateway, network integration, and dashboards like EPMS or DCIM are functioning correctly. Alarm thresholds, trend data storage, and event timestamps must all be validated. Additionally, mapping these monitoring points to the corresponding battery strings, UPS systems, and physical rooms is crucial for operational clarity. When it comes to level gate proof, there are multiple layers of testing. First, we confirm that the points list, naming conventions, topology, and alarm philosophy are all in place at level 0. Then, at level 1, we conduct factory acceptance tests on the monitors and gateways, simulating communications. Level 2A focuses on sensor placement, labeling, addressing, and cable routing, while 2B checks the accuracy of point-to-point connections, scaling, and offline alarm functionality. Level 3 is about capturing baseline data and simulating threshold alarms. And finally, levels 4 and 5 involve validating battery discharge correlation and testing for communication loss. For acceptance evidence, We collect essential documentation and proof points. This includes a string and cell mapping register along with a baseline report, alarm screenshots complete with timestamps and operator acknowledgments, and exported trend data from discharge or autonomy tests. We also need to demonstrate network failover capabilities and provide evidence of loss of communications handling. Additionally, operator training completion and user acceptance of the dashboard are critical milestones. A common pitfall in battery monitoring system commissioning is failing to consider a monitoring point complete until it's physically mapped to its actual cell or string and validated during a real operational event. This step ensures the data is truly reflective of the system status and can be trusted for decision-making. Now, let's focus on Section D, which covers containerized plant commissioning. This involves several key stages to ensure the factory-built electrical plant is ready for operation. First, package-level factory acceptance testing, or FAT, is performed to verify that the plant meets all design and performance specifications before it leaves a factory. Next, delivery quality assurance is crucial to ensure the plant arrives on site without damage and complies with all contractual requirements. Once on site, integration with existing systems through site acceptance testing, or SAT, and installation and site testing, IST, is essential to confirm everything works seamlessly together. Following the guidelines laid out in the MEP testing and commissioning playbook will help ensure a smooth and successful commissioning process. This slide outlines a commissioning strategy for containerized plants, treating each container as both individual equipment and a mini plant room with multiple interfaces: electrical, mechanical, fire, controls, and access. The process begins with design freeze to lock-in interfaces, followed by integrated factory acceptance testing and site integration testing to validate performance in controlled environments. Delivery quality assurance involves transport checks to ensure the container arrives undamaged. On-site installation includes red tag inspections to verify proper placement and connection. Static tests, identified with yellow tags, focus on confirming system readiness before startup, where local systems are activated and checked. System acceptance testing and integrated system testing, represented by blue and white tags, further validate functionality. Finally, handover includes training to ensure operators understand the system. Supporting evidence is crucial and categorized into package, site, and integration documentation. The package evidence encompasses the integrated FAT/SIT dossier, closure factory punch lists, configuration freezes, transportation records, and asset registers. Site evidence covers foundation work, anchoring, alignment, interfaces for cables, pipes, and fire stops, readiness of HVAC and fire suppression systems, live control systems with networking, and emergency access and signage. Integration evidence involves point-to-point connections for EPMS, BMS, and fire alarm systems, fire cause and effect logic, source transfer and load bank links, container smoke, heat, and ventilation responses, as well as event timestamp proof during integrated system testing. It's important to note that container acceptance is not considered complete solely at factory FAT. The site-specific interfaces, life safety responses, and integrated power and cooling behavior must be fully proven after installation, emphasizing thorough testing beyond the factory environment to ensure safe and reliable operation. This slide covers the testing and commissioning of a containerized 20 kV medium voltage switchgear unit. The main objective here is to ensure that the switchgear container functions as a safe, well-ventilated, monitored, and fire-protected electrical room. Starting with the scope, it includes the medium voltage switchgear itself, relay panels, current and voltage transformers, and the cable termination area. We also focus on the 110 VDC VRLA battery and charger, lighting, power, and auxiliary panels. Safety and operational systems like the arc flash relief duct, cooling unit, smoke and heat detection, and clean suppression are all part of this scope. Lastly, control and communication systems such as the ACMP or PLC-HMI, EPMS, fire alarm system, building management system communications, and access controls are critical components. Regarding the level gate proofs, we have several stages that verify different aspects of the installation. Level 0 covers the ratings, arc relief, ventilation, fire rating, and maintainability. Level 1 involves an integrated factory acceptance test with all major components like switchgear, DC power, HVAC, fire alarm, and control modules. Level 2 is split into two parts: The first confirms proper container placement, anchoring, access, cable entries, and labeling, while the second focuses on testing the MV system, DC system, HVAC checks, and point-to-point verification of fire alarm and control systems. Level 3 includes energization, relay injection testing, DC power autonomy, and HVAC operation. Finally, Levels 4 and 5 simulate failure scenarios, such as breaker failure, DC power loss, cooling loss, fire alarm activation, and source transfer situations. For acceptance evidence, this process generates several key documents and records: a comprehensive integrated FAT and site integration test dossier with issue closure, detailed medium voltage test reports, relay settings, and evidence of DC autonomy. Test records for HVAC, fire alarm, and suppression systems are maintained alongside screenshots and time-stamped logs for control panel and management systems like ACMP, EPMS, and BMS. Additionally, proof of access controls, signage, and emergency procedure training is essential. One common trap to avoid is underestimating the importance of container auxiliary systems. These are not secondary support. If DC power, cooling, or suppression systems fail, the entire medium voltage plant could become unavailable. It's crucial to treat these auxiliary systems with the same level of attention and rigor as the main electrical equipment to ensure reliable operation and safety. Overall, this comprehensive approach ensures the switchgear container meets all operational, safety, and reliability requirements before being accepted into service. This slide focuses on the testing and commissioning of containerized transformers and medium voltage 20 kV ring main units, or RMUs. The objective here is to ensure that the transformer and RMU container is safe for medium voltage isolation, transformation, cooling, and fire response. First, let's look at the commissioning scope. It covers the medium voltage RMU, the transformer compartment, and the low voltage air circuit breakers and interfaces. It includes ventilation and natural cooling systems, temperature monitoring, and fire segregation. The electrical supply systems at 110 VDC, lighting, power controls including the air circuit breaker management platform, and local alarms are also within scope. Furthermore, fire suppression systems like clean agent or other approved methods, along with their interface to the fire alarm system, are essential components of the commissioning. Next, the level gate proofs define the stages of testing and inspection. Level 0 involves compartment segregation, rating, ventilation, and protection studies. Level 1 includes factory integrated tests covering RMU, transformer, battery DC supply, ventilation, and fire alarm systems. Level 2 is split into two parts: one for transport inspection, container alignment, cable entries, and grounding, and the other for medium voltage and low voltage tests, transformer assessments, control wiring, and suppression checks. Level 3 focuses on energization and no-load soak tests, DC autonomy, and ventilation controls. Finally, Levels 4 and 5 cover load soak tests, inter-trip functionalities, high temperature, and fire mode scenarios. The acceptance evidence required includes factory test certificates and the container's factory acceptance test. Transformer tests such as dry or oil temperature monitoring systems and RMU test packages are critical. Continuous temperature trend monitoring, fan and ventilation operation evidence, and alarm records are necessary. Additionally, records from the fire alarm system, air circuit breaker management platform, building management system, and emergency power management system must be documented. Emergency access procedures, isolation protocols, and training sign-offs complete the acceptance criteria. Lastly, a common pitfall to watch out for is the assumption that one container-level acceptance tag is sufficient. It's important to maintain separate acceptance evidence for both the transformer and the RMU components, as a container tag does not replace detailed component-level acceptance. This ensures thorough verification and reliable commissioning of the entire unit. This slide focuses on the testing and commissioning of the Containerized Powertrain Unit, or PTU, highlighting the key areas we need to verify to ensure it functions safely and reliably. The main objective is to prove that the PTU delivers critical low-voltage power through the main switchboard, automatic transfer switches, uninterruptible power supplies, and batteries, all while integrating full safety features. The commissioning scope covers important components, such as the main LV switchboard, ATS, UPS with static transfer switches and bypass functionality, lithium battery systems complete with DC protection and monitoring, as well as cooling systems, auxiliary power, lighting, and fire detection and suppression equipment. We also look at ventilation systems, motorized fire dampers, and load bank connections to ensure comprehensive coverage. We approach this through a series of level gate proofs. At the initial levels, we focus on documentation and integration tests, including single-line diagrams, sequences of operations, and system autonomy. As we progress, we perform factory and site acceptance testing, verifying placements, cable entries, earthing, fire stops, and ventilation paths. Further levels involve detailed electrical checks like insulation resistance and torque, point-to-point verification for fire alarm systems and control panels, followed by energization and system startups. The final stage is simulate utility loss, testing UPS autonomy, STS transfers, fire mode activations, and load bank performance tests. Our acceptance evidence includes factory acceptance tests with fixed settings, detailed records from UPS and transfer systems, baseline battery tests, as well as reports on switchboards and cable assemblies. Fire suppression cause and effect logic and operator control monitoring logs are reviewed, alongside a comprehensive event chronology, supported by emergency power management system data. One common challenge during PTU acceptance is the need to simultaneously validate power continuity, battery safety, cooling performance, and fire response. Balancing these aspects requires careful coordination and thorough testing to ensure everything works seamlessly together for reliable emergency power delivery. On this final slide, we focus on commissioning of containerized generators and load banks. The main objective here is to confirm that the generator containers and load bank interfaces effectively support emergency operation and enable repeatable load testing. The commissioning scope covers a wide range of components. This includes a diesel genset itself, along with the acoustic enclosure, muffler, flue, and ventilation systems. We also look at auxiliary systems like dual starter batteries, the fuel system, water mist or approved suppression systems, and fire dampers. Integration points such as a generator control panel or PLC, EPMS, BMS, and FAS interfaces, as well as the remote camlock and load bank interfaces, are also tested. Additionally, the containerized load bank comes with remote controls, cooling systems, and communication links that need thorough validation. The level gate proof process is structured in several stages. Starting with L0, we verify ratings, exhaust, ventilation, fuel runtime, fire protection, and acoustics. L1 involves factory load runs, control system checks, shutdown functions, and testing the fire and HVAC packages. L2A and L2B focus on physical placement, piping, cables, damper operations, inspection for leaks, pressure tests, fire detection, and wiring continuity. L3 tests the first startup, safety shutdowns, fuel pump function, and alarms. Finally, L4 and L5 cover load stepping, source failure responses, cascade operation, fuel failure scenarios, and load bank integration. For acceptance evidence, documentation is critical. This includes factory load run records and controller settings, fuel pressure and leak reports, as well as fuel quality tests, load bank performance logs and power quality measurements, fire and ventilation cause and effect analysis, and records of noise, exhaust, thermal performance, and operator training. A common pitfall to avoid is assuming that a successful engine load run alone represents full acceptance of the generator container. Instead, commissioning must prove all supporting systems function properly to ensure the system is fully operational and reliable.